Hello students, good morning. Good morning to you all. I hope all are doing good and studying good, following the classes properly and you're learning concepts properly and in a easier way. Okay. Good morning, Ramesh. Avanti, good morning. Ikshita, good morning. Okay, Devadarshini, good morning. Kiranya, good morning. I am superb, I am good. Yes, I am very happy to see your messages and your wishes. Okay, shall we start the class? Dhruti, good morning. Okay, Sakura, yes, I am good. I am good. Spurti, good morning. Okay, Varshita, good morning. Varshini, good morning. Okay, uh, I hope it's time to start the class. In last class, we have studied about overlapping of atomic orbitals concept. And afterwards, I have given introduction about sigma bond formation and pi bond formation, right? Let's continue discussion about sigma bond and pi bond. I'll try to explain some important properties of sigma bond and followed by pi bond. Right? Afterwards, we will solve some questions related to counting total number of sigma bonds and pi bonds. And if possible, we will try to work on formation of some important molecules. Even in today's class also, I wanted to stop the chart. So today, I'll definitely allot a proper dedicated time for doubt session. Okay. Before ending this session, I'll try to give at least 10 minutes for doubts clarification. Okay? Okay. Fine. I hope you are with the books and I think you are having notebook and pen. I heard like yesterday you have taken the classes properly and you listened properly. You have followed the classes properly. Right? Okay? Let's start the class. In last class, I have introduced sigma bond. And we have concluded that sigma bond formation takes place either due to axial overlapping of atomic orbitals or linear overlapping or head-on overlapping or end-to-end overlapping. I have given three possible axial overlappings. Okay, I have given SS overlapping leads to form sigma bond, SP overlapping leads to sigma bond, even PP overlapping leads to sigma bond. We have a sigma bond even in combinations with d orbitals also. I am not going to give those details in bridge course. Okay. So primarily we need just only three combinations, right? So I am continuing some other points related to sigma bond. Sigma bond is a strong bond okay. How we can conclude the sigma bond as a strong bond, I'll explain after giving information about even pi bond also. Okay. Now, since it is a strong bond, hence we can consider it as a stable bond. Next, point number 3. Sigma bond exists independently. I can also say the first bond formed between any two atoms must be sigma bond, right? Electron density of sigma bond present along the axis. I can also write spherically, symmetrical I can write, but enough along the axis, right? Since electron density is along the axis, free rotation along sigma bond is possible. Free rotation along sigma bond is possible. What I mean to say over here, if I am having a bond between, let's say, carbon-carbon bond, if it is a sigma bond, since electron density is spherically symmetric around the nuclear axis, then you can rotate the sigma bond freely. So, free rotation is allowed. There is no restriction of rotation of sigma bond. Okay? Why I am mentioning here free rotation? In future, when you are taking the NEET course, we will talk a topic which is called as geometrical isomerism. Under geometrical isomerism, this kind of discussion comes. Okay? Right. So, you can rotate the sigma bond freely. Next point. Next point. Sigma electrons are not delocalized or just localized between two atoms. Localized means considering a bond between, let's say, A and B. If you have a bond between A and B, the bonded electrons should remain exactly between two atoms. Of course, if it is a polar covalent bond, the electron density partially shifts towards any one of the atom, but not completely. Complete transfer won't take place. So, the electron density remains between two atoms only. It is localized or present between two atoms. These electrons you can't shift from one bond to other bond. Okay? The sigma bonded electrons are localized between bonded atoms. Fine. Next one. Sigma bond can be formed or formation takes place with atomic orbitals as well as atomic orbitals even hybrid orbitals also can be formed. That means hybrid orbitals can form sigma bond. Atomic orbitals also can lead to form sigma bond. In last class we have discussed the sigma bond between s orbital and s orbital, means these both are atomic orbitals only. If you take s atomic orbital and p orbital, here also these are atomic orbitals. Sigma bond formation takes place either with atomic orbitals or with hybrid orbitals. We will talk about hybrid orbitals under hybridization concept. Wait for one more day. Okay? Probably from Monday onwards, I will try to introduce hybridization, most important topic in chemical bonding chapter. Okay? With this, I am going to stop the points about sigma bond. Okay? Sigma bond is a strong bond, and the first bond which is formed between any two atoms must be sigma bond. Okay? Right. Sigma bond is stronger bond and stable bond. Let's move on to the pi bond. Shall we move on to the pi bond? I hope these points are clear to you. Okay, I hope these points are clear. I have given some important points related to sigma bond. Now we will talk about the important characteristics or points about pi bond. Okay, next. Now coming to the case of pi bond, as I have given one illustration example for the formation of pi bond as PP parallel overlapping, I mentioned PP parallel overlapping. Leads to form a pi bond. If a pi bond is formed between two p orbitals, if I am considering p orbital, if I am trying to make the pi bond, this pi bond is considered to be p pi bond. Pi bond is represented as p pi. Whenever I am referring a pi bond can be expected to be formed between two p orbitals, or there is a possibility of formation of pi bond between p orbital and d orbital. If the pi bond is formed between p orbital and d orbital, it is represented as p pi d pi bond. If the pi bond is expected to be formed between two d orbitals, we can consider or we can represent the pi bond as d pi. Okay, here it means d pi means pi bond is formed between two d orbitals. P pi d pi, or I can also represent it as d pi p pi. D pi p pi means pi bond which is formed between one d orbital and one p orbital. What do you mean by p pi p pi? It means pi bond formation takes place between two p orbitals. Okay, hence pi bond can be expected between two p orbitals or one p orbital with d orbital, or it can be formed between even two d orbitals also. Is this point clear? Next, moving on to the characteristics of the pi bond. Let me write pi bond is a weak bond. Pi bond is a weak bond. Why the bond is weak bond? As we know, the overlapping strength is less. To decide the strength of any bond, we need to consider the effect of overlapping. Okay, effect of overlapping is inferred by the region of overlapping. Okay, let me say, for example, if you take two p orbitals, let me say p orbitals, if two p orbitals are trying to overlap along the axis, this bond we can refer it as a sigma bond. If you consider the overlapping region of combination of these two p orbitals is more. Okay, overlapping region is more, or the area or the space which is involved in overlapping is more, then we can consider it as strength of this bond is more. Strength is more. Strength is more. When it comes to the pi bond, these two p orbitals are perpendicular to the nuclear axis and these are trying to overlap laterally. This is considered as sidewise overlapping. So if I am considering sidewise overlapping, the space or the region of overlapping or common region is very less or less compared to sigma bond. Hence we can say that sigma bond is stronger than pi bond. Why sigma bond is stronger than pi bond? Simple point. If I am considering the space which is involved in the overlapping, or the common space or common region which is involved in the overlapping of two atomic orbitals is less for pi bond formation compared to sigma bond formation. Therefore, strength of the bond I can write it as strength of the bond. Very important point. Strength, this is one of the parameter to decide the strength of the bond. We can have some other parameters also, and we will talk about those parameters in upcoming classes or if possible within this class. Strength of the bond is directly proportional to area or the space which is involved in overlapping. Okay, region of, I can say, common region or region of overlapping, region which is involved in overlapping. I mean to say, here the electron density, okay, or the space, okay, which is involved in overlapping, right? You can also decide the strength of the bond. One more parameter I am trying to give. Strength of the bond is also proportional to or inversely proportional to, I can say, 1 by principal quantum number. Okay, as the principal quantum number increases, strength of the bond decreases. This is also very important parameter to decide the strength of the bond. I hope these points are clear. I was trying to say pi bond is a weak bond. You may have doubts, sir, why pi bond is a weak bond? Even pi bond is also formed by overlapping of two atomic orbitals only, but you need to check the region which is involved in overlapping. The region of overlapping for pi bond is lesser compared to sigma bond. Hence, we can conclude that pi bond is weaker than sigma bond. Okay, then we will discuss some other points which are supporting the information of the second point. Strength of the bond can also be decided based on principal quantum number. Okay, if it is the case, I will try to give a point here. I thought this is the right time to deliver this point after giving the inputs about knowing strength of the bond. Okay, I think you can answer this point easily. Now try to answer this point. Fine, try to answer this point. If I have given, let's say SS overlapping, considering sigma bond possibility, SP overlapping, PP overlapping. Dear students, my dear students, can anyone tell me these three combinations are leading to form a sigma bond, but I need to know which sigma bond is stronger sigma bond or which combination or which overlapping leads to strong sigma bond. Okay? If you observe the common region which is involved in PP overlapping is more. Okay, I showed the overlapping between two p orbitals axially. I can quote that here PP overlapping. I suggest sigma PP which is greater than sigma SP overlapping which is greater than sigma SS overlapping. This point is very important point. If someone is asking me to write the sigma PP I mentioned and pi PP I mentioned, or this can be referred as P pi, P pi. Out of these two, which bond is expected to be strong bond? Can anyone tell me which bond is expected to be strong bond? Obviously, the sigma bond is stronger than pi bond. This is question number 1 or point number 1. Point number 2. Point number 3, if I am having, let's say, for example, pi bond between two p orbitals, let's say 2p, 2p and 3p, I refer it as 2p, 3p and 3p, 3p. If I am considering the case of sigma, can anyone tell me the order of strength of these three sigma bonds supporting the second statement which I have given? As the principal quantum number increases, orbital size also increases, orbital diffused nature increases, then the region which is involved in overlapping obviously decreases. As the size of the orbital increases, diffused, I mean electron cloud is occupying in more space, right? Then the region which is involved in overlapping obviously decreases, and thereby the strength of the bond obviously decreases. Okay, otherwise you can directly apply this point. Strength of the bond is inversely proportional to principal quantum number. As the principal quantum number increases, strength of the bond decreases. Okay, this point is also very important point. Okay, so coming to the common points which will be discussed under pi bond, the only important point which I wanted to mention here in this case is pi bond is weak bond. Weak bond. If it is a weak bond, I can say it is less stable compared to sigma bond. If I can say if it is weaker, I told it is less stable. If it is less stable, it's supposed to be more reactive. Therefore, the pi bond is more reactive. I am writing these points over here. Pi bond is more reactive. And next I am trying to give you other points also. Pi bonded electron density. Pi bond electron density is above and below the nuclear axis. Okay, this I have showed in the last class itself. Okay, now moving on to the next very important point. Since electron cloud is above and below the plane, there is a restriction for free rotation, and hence I wanted to write this point. So free rotation along pi bond is restricted. Why there is a restriction for free rotation along pi bond? Very simple topic, very simple story. There is a cloud of electron density above the nuclear axis and below the nuclear axis. If I am trying to rotate, the pi electron density can be deformed. Therefore, I will not allow if someone is trying to rotate the pi bond. Why? Because it causes deformation of the bond. Okay, therefore the pi bond does not allow for free rotation, but sigma bond can be freely rotated because electron density is along the nuclear axis. When I am trying to talk about the pi bond, let us assume, consider there is electron density above the plane and below the plane. If I am trying to rotate the pi bond, the pi electron density can be deformed. That is the reason why if any system is associated with pi bond, it does not allow for free rotation. I hope this point is clear. Okay, and one more point I wanted to quote here. Pi bonded electrons can be delocalized. Pi electrons can be delocalized if they satisfies the condition. Delocalized. Okay, there is a very important topic in organic chemistry, that is resonance concept. Okay, under resonance concept we will talk about delocalization of pi electrons. For delocalization of pi electrons, there must be conjugation which exists. Okay, all these details we will discuss in regular classes. Therefore, pi electrons can be delocalized. Now, pi bond, this is most important, very important point. Pi bond formation is possible only between pure atomic orbitals. Why I am trying to mention pure atomic orbitals? With this I wanted to quote one point. Hybrid orbitals, HO means hybrid orbitals. I will explain the topic hybridization. hybrid orbitals do not form pi bond. Pi bond. Therefore, pi bonded orbitals cannot be counted for hybridization because pi bond formation involves only with the atomic orbitals. Atomic orbitals are allowed to form pi bond. Hybrid orbitals are not allowed to form pi bond. It means hybrid orbitals do not form pi bond. Hybrid orbitals can form or can leads to form sigma bond. Okay, I hope all these points are clear. So if the points are clear, okay, let's move on to the next point, right? Okay, I was trying to explain some of the important characteristics of sigma and pi bond, out of which three main conclusion points I wanted to repeat once again. Sigma bond is a strong bond and hence which is a stable bond. Okay, sigma bond or the electron density along the sigma bond can be freely rotated. Fine. And sigma bonded electrons are localized between only two atoms. Sigma bonded electrons cannot be delocalized. Delocalized means let us suppose I am standing over here. Okay, I can move from here to here, here to here. I cannot delocalize my place. Okay, if I am standing only at this particular position or within the constraint of like let's within the feet, let us assume. Okay, if I am standing only at this particular position, I am localized. If I am moving freely from one place to another place or one bond to another bond, this is considered as delocalization. So delocalization is possible for pi electrons. Sigma electrons cannot be delocalized. Okay, I think points are clear. Let's move on to the next point. Okay, I think the strength of the bond story also clear. I was saying like if you wanted to like predict the strength of the bond, you need to check out certain parameters. You need to check the overlapping region between two atomic orbitals, and sometimes you need to check out the principal quantum number also. Okay, right. Let's try to understand the formation of N2 molecule, okay, and O2 molecule. Let's say first we'll talk about formation of. Some people may be having doubt like, sir, if at all any possibility of forming bonds between two atoms, how many maximum number of bonds can be possible? Like with this things will be completely clear. Formation of N2 molecule. Okay, so two nitrogen atoms should be brought together for bonding. Let me write the electronic configuration of nitrogen. Atomic number of nitrogen is 7 and its electronic configuration is 1s2, 2s2, 2p3. And as we know that the electrons from valence shell can participate in bonding. The inner shell electrons is not easy for bonding. It's a very simple logic. Okay, if the electrons density is far from the nucleus, you can reorganize them easily. The electrons which are closer to the nucleus are strongly bounded to the nucleus. You cannot remove the electrons, you cannot even try to add easily. That's what I am saying. Okay, okay, that is other story. So what I was trying to say, the electrons which are from valence shell can only participate in bonding. Is this point clear? The electrons from valence shell or outermost shell are allowed to enter into the bonding. Okay, here the valence shell for nitrogen is second orbit. Okay, the valence shell configuration of nitrogen is 2s2, 2p3. Let me write with box representation. 2s has 2 electrons and 2p has, Hund's uncle is very near to us. We need to follow the instructions given by Hund's uncle. Okay, I was trying to say he is very strict person. If you are not obeying his role, he felt very bad. Okay, sometimes you can tap. Okay, that I am trying to fill the electrons based on Hund's rule. Hund's rule is the story of, I told, degenerate orbitals. Whenever you are filling the electrons in degenerate orbitals, each orbital should be filled with one electron. Okay, then only you are supposed to start pairing. This is the story of one nitrogen atom, and second nitrogen atom also the same story. Therefore, my dear students, listen carefully. Each nitrogen has 2 electrons in 2s orbital and 3 singly occupied electrons in 2p orbital. Let's try to write the situation here. Okay, and nitrogen has 3 p orbitals. Let's try to fix this orbital as, let's say, z axis. Okay, let me write the z axis in this way. Let's say, okay na, I think this is for one nitrogen story. The other nitrogen story I am trying to write over here. Okay, this is nitrogen's pz orbital. Is it fine? Okay, since I have taken z axis as nuclear axis, so along the nuclear axis, pz orbital of nitrogens or along the axis. Now what about the rest 2p orbitals? As we know that px and py are the remaining 2 orbitals. Let me write the remaining orbitals in this way, and then the other one I'll try to write with the other color. Okay na? Right? Very good. And this is let me say, and good, done. Okay, so you can label this as, let's say, py, and this one will also be py, and try to label this as pz, and even this is also pz. Okay, my dear students, I am trying to represent even the py orbital also. This is py orbital. Py orbitals of 2 nitrogen atoms are perpendicular to the nuclear axis, and of course which are parallel together. And even the pz orbitals of 2 nitrogen atoms are perpendicular to the nuclear axis, and obviously they are parallel to each other. Now tell me students, between pz and pz, what kind of overlapping can be expected? It is axial overlapping, right? Or linear overlapping, or head-on overlapping, or end-to-end overlapping, which must leads to form sigma bond. Then now I think you will answer this point very easily. Now the py orbital of one nitrogen and the other nitrogen are parallel together. That leads to form what kind of bond? Obviously pi bond. Now if you observe carefully, the 2 pz orbitals of 2 nitrogen atoms are again perpendicular to the nuclear axis and parallel to each other. Therefore that leads to form what bond? Pi bond again. Therefore, if you can summarize and write 2 nitrogens in this way, nitrogen, nitrogen, in between 2 nitrogen atoms, the first bond formed is sigma bond. I try to fix like this, and the rest of the bonds are pi bonds. Some students might be having doubts like, okay, if a triple bond is present, so out of triple bond, how many are considered as sigma bond? Only one sigma bond. The rest of the 2 bonds are pi bonds. Okay, so why I have given this representation? We are going to count the total number of sigma and pi bonds. If there is a triple bond in a given compound, you have to consider one of the bond as sigma bond, triple bond, one of the bond as sigma bond, and the rest bonds are pi bonds. If I am having, let's say, a double bond, I means 2 lines. Okay, we have considered, we have discussed in last class. Out of 2, one bond as sigma bond and the other bond is pi bond. If I am having only single line, the bond must be sigma bond. Why? Because in organic chemistry, sometimes we used to refer the compounds with bond line representation. we will try to represent the bonding only with the lines. In such cases, you might be knowing about the triple bond, double bond and single bond. Triple bond means considering one sigma bond and two pi bonds. This is double covalent bond or double bond. It contains only one sigma bond and one pi bond. And if you observe anywhere in any compound, a single line is representing only sigma bond. I hope these points are clear. Okay, are these points clear? If these points are clear, you must be ready in counting sigma and pi bonds in a given compound. Are you ready? Counting sigma and pi bonds. I hope this formation of N2 is clear. I was trying to say nitrogen, its valence shell configuration, we have 2s2, 2p3. Okay, you can write the two electrons which are present in the 2s orbital as a lone pair. This is called as lone pair. Lone pair means non-bonded electrons. Let me write lone pair. Lone pair means pair of electrons which are not involved in bonding, which are not involved in bonding, not involved in bonding. And hence these can also be written as non-bonded electrons. Non-bonded electrons. These terms you must be very clear. Lone pair. Okay, each nitrogen has one lone pair. Each nitrogen has one lone pair. What do you mean by lone pair? Pair of electrons which are not involved in bonding. Hence, those can also be called as non-bonded electrons. I think points are clear. Okay, each nitrogen has one lone pair. Okay, and total 3 bonds are present between 2 nitrogen atoms, out of which one is sigma bond, the rest bonds are pi bonds. Why only one sigma bond is allowed to form between any 2 atoms? It is very simple. Okay, how many orbitals you can write only along the axis? Only one orbital can be written along the nuclear axis, and the rest 2 orbitals must be perpendicular to the nuclear axis. Of course, if the orbitals are perpendicular to the nuclear axis, they must be parallel to each other. And hence, only sigma bond, only one sigma bond is possible between atoms and 2 pi bonds can be possible. Okay, by considering example as N2. Okay, shall we start counting the total sigma and pi bonds for given examples? Let's move on to the examples. Count or calculate, count total number of sigma and pi bonds for the following. I hope you can count very easily. Let me start with very simple example, methane. And I am trying to give the formulas. Ethane, ethene. I have given the names of these compounds also, and this is ethyne and benzene. I think you might be knowing about the compound benzene. Benzene is having molecular formula C6H6. Benzene is very important compound in especially organic chemistry. Benzene is cyclic 6-membered ring with alternative pi bonds. This is benzene. I think representation of benzene, different stories we have. You can also represent like this. This is the concept of resonance. There you must study few things. I can also represent like this. Any one of these are. This is more accurate representation. This is true structure. These both are hypothetical structure. That is different story. Now start counting the total number of sigma bonds and pi bonds in benzene. Let's start. Okay. Counting total number of sigma and pi bonds in benzene. Are you counting? I hope you are counting. There is pi bond over here, pi bond over here, pi bond over here. So this is the place where you can write the carbon. This is the place of carbon actually. This is also carbon, and carbon over here, carbon. Total number of carbons are 6 as you know. Okay, and we have 6 hydrogens. Okay, now I think just by looking the structure, you may give different answer. People who are wise enough to identify hydrogen atoms also give the correct answer. Okay, options, you can frame the options anyway. So if you just as it is count, this is considered 2 lines, I have 1 sigma and 1 pi. If you count in this manner, this is only sigma and sigma pi, sigma, sigma pi and sigma. You may be having only 6 sigma, and some people can write 6 sigma bonds and 3 pi bonds, which is wrong option. Okay, so people, we know very well, carbon is tetravalent. Carbon has to account for 4 bonds. If you write 4 bonds for carbon, now what bond is expected between carbon and hydrogen? There must be sigma bond. Now in total, how many sigma bonds are present? How many sigma bonds and how many pi bonds you can count? Pi bonds, it is very easy to count. 3 pi bonds, it is for sure. Then how many sigma bonds are present in benzene compound? Okay, I hope you are giving the answers. Yes, with this I will close the class. Okay, if anyone has any doubts, I think you can raise your queries, you can raise your doubts, so that I will clear the doubts. I will try to give the worksheet based on counting sigma bonds and pi bonds, and the questions which are related to overlapping of atomic orbitals and formation of sigma and pi bonds. Okay, right, how much answer you are getting, my dear students? Here count the sigma bonds: 1, 2, 3, 4, 5 and 6, 7, 8, 9, 10, 11 and 12. So in total, how many? 12 sigma bonds we have, and how many pi bonds? 3 pi bonds. Okay, so can anyone count the total number of sigma bonds and pi bonds for D option? Okay, we have completed E, and you need to count for the D, question D. Like, these are not options actually, these are each and every question I have given. Methane you need to count, ethane you need to count, ethane and ethane also you have to count. Okay, I hope you are getting the answer for benzene. Are you getting the answer for benzene? Total sigma and pi bonds you can count easily. Okay, it is very simple question actually. I have given representations of benzene. Benzene can be represented by either by this one or this one, but actually the true structure of benzene is this one. I think somewhere you will find the circle like. Okay, this is considered as resonance hybrid. Those details we will study in future classes, in offline classes only. Okay, fine. Are you counting the total number of sigma and pi bonds in C2H2? Okay, just a second, I will try to open the chat box. Okay, so meanwhile you can have your questions and you can ask your questions, right? Chat box. Okay. Yeah, any doubts, students? If you have any doubts, you can ask me. I think chat box is open now. Chat box is open. You can ask your queries. Okay. Please open faster side, sir. Okay, fastest side. I think I need to take the screenshot over there. Past page you want, right? Okay. I think points are clear. I hope you got the information about formation of sigma bond and formation of pi bond. Yeah, day 2 bond we will study. Don't worry. Day 2 bond could be a sigma bond. Okay, or even. Right, that we will discuss. Don't worry. In CH4, 4 sigma bonds. Day 2 bond we'll discuss. No need to worry. We have completed covalent bonding. In previous classes we have completed pi bonding. Ionic bonding. I think Last two classes we were trying to discuss about sigma bonds. We have completed about the covalent bonding, sigma and pi bonding, all the stuff. We are left with day 2 bond. Okay, so day 2 bond we will discuss. Okay, day 2 bond is also kind of special covalent bond only. Sorry for misinterpretation, it is the first slide. Okay, just a second, I will go for first slide. I think, is it the one, or I think first slide is, sorry, this one I guess. Okay, you can take the screenshot quickly. Have you taken? Carbon forms 4 bonds. Yes, 4 bonds are there. Okay, check out. Carbon valency is only 4. So in benzene, carbon is involved with 4 bonds. Okay, if your doubt is why can't you expect 4 bonds between 2 bonded atoms, you can never expect 4 bonds between 2 atoms. The maximum number of bonds which are allowed to between any 2 atoms is 3. Okay, 1 sigma bond and 2 pi bonds. Sir, can you explain once again the bonds that how to form or how to write the please? Okay, I'll write. Okay, if you take an example, I'll take the example. I think you have taken the screenshot. Okay, right. Now coming to let's simple example for C2H2. C2H2, if you have carbon, 2 carbons we have, each carbon is bonded to 1 hydrogen, and as we know carbon is tetravalent, then still 3 bonds are required to satisfy tetravalency. Okay, now you can count comfortably. Okay, here 3 lines I have, out of which there is 1 sigma bond and how many pi bonds? 2 pi bonds, right? Here there is 1 sigma bond and here there is 1 sigma bond. In total I have 3 sigma bonds and how many pi bonds? 2 pi bonds in ethine. You can count the bonds in this manner. Okay, okay. Devadarshini, okay, okay, right. You can count comfortably. Okay, with this I wanted to stop for today's class. I hope things are clear. You are learning the concepts properly and try to revise the concepts, okay, and try to work questions based on the concepts. With this, I wanted to close for today's session. Okay, that's all for today's class. If you have any other doubts, you can ask me during the next class. Okay. So thank you and have a nice day. And once again I am trying to remind, if you like the video, and please press the like button and forward and subscribe the video, subscribe the channel. You can forward the video to your friends so that they can also be benefited. Once again, thank you very much and have a